All right. So let's go back and start. There is the next. I don't have too many topics to talk about now in this story. I want to tell you there's a paper. Could we settle down, please? Thank you. There's a nice paper, Learning to Personalize from Observational Data by Nathan Callis, which is interesting. To basically what he's trying to do is that he's got a data set where he looked at some confounding variables xi's. There were n users in the data set. For each of those users you had a variable xi, which was the confounding variable. You had the treatment level that they were given, ti, and the outcome that you got, yi. And the goal that they wanted to compute was to find a mapping from the confounding variables x to a treatment condition 1 through capital T, capital tau. So think about the case where maybe these people are suffering from different kinds of cancer, or maybe they have tumors in the same area but they have different kinds of tumors. These people historically had been treated by giving them different kinds of treatments, and the outcomes from those treatments are known. Now what you want to do is look at a new patient comes in, and you want to look at their characteristics of their tumor and map it to one of tau different treatments that potentially can help them cure that tumor. And the goal is to maximize this function g of f, where f is this mapping function, which is defined as the expected value of the outcome that you get from the treatment that this person x has, this person with confounding variables x has been assigned to. So the way to think about it is that you've got the tumor's characteristics are known. You want to map the tumor's characteristics to a treatment program such that the expected value is maximized. Okay, expected value from the treatment is maximized. Wow, this interference is quite high. So mu t, remember mu t, which is the expected value of ct, can be written as the expected value of ity divided by qtx. So now if you look at this particular quantity, what has happened is that this function gfx has been written as expected value of the indicator function, that t is equal to fx times y divided by qtx. This is exactly the same statement as this one, except that you have cfx, and for every value of t you know that this ct is exactly equal to that. So you put, instead of t you put fx and you get this outcome. So now what he wants to do is convert this problem into a classical classification problem. So the point of this exercise that I'm trying to show you is the connection. The causality is important, but the other thing that I wanted to show you in this module is that there is a connection between what is happening in causality. The point that I'm trying to make here is I want you to understand what happened over here, because then later on I'll just talk a little bit more about how this thing has transformed. Remember, so think about a classical classification problem. The classification problem is that you've got some input, you want a mapping from that input which maps it into some set 1 through tau classes, and you want to minimize some error. Typically you want to minimize maybe the error between the outcome minus f of x, the true outcome minus your outcome, or some function you want to minimize that the outcome is not equal to f of x, or you want to maximize the expected value of the indicator function that y is equal to f of x. Right? So that's typically what a classification problem does. So what in this paper what he did was that he wanted to transform this trying to assign treatments to different people into a classification problem. And instead of using one of these kinds of classification metrics, he's using this classification metric. So what is the indicator function? T is equal to fx, y divided by qtx. This is just some other function that depends on this function f of x. Y is known, tx is known. You want to get this function and be able to learn from there, and what he wants to do is transform this into a classical looking classification problem, and then use the methodological ideas of classification problems to solve this problem. And this is what ends up doing. So you can show just by the same conditional expectation that this expectation of it equals fx divided by qtx is equal to 1.
So what is the meaning of personalization?
So personalization is that x is the outcome. So the way to think about this, a person comes in, you made some measurements on their tumor, and then you're going to decide what kind of treatment that person is going to get. This X could be some genetic screening that you have done, you have looked at their x-rays, you have look at their various kinds of other kinds of indicators about them, and the treatment is actually personalized to this person as opposed to necessarily just having a generic treatment exercise. Okay? So for all eta, since this quantity is equal to 1, g of f, I'm just adding and subtracting eta. Except for eta, I wrote this quantity. I took this and put it into the objective, and you get the indicator function of t is equal to fx, y minus eta divided by qtx plus eta. For nu greater than 0, define rf to be 1 over nu, this factor. And if you calculate what happened over here, if you put in this gf over here, you end up getting that this risk factor is nothing but the expected value of f of x not equal to t, y minus eta divided by nu qtx. So now you're minimizing the classification risk rf is equivalent to maximizing gf. The empirical estimate can be computed by looking at the f. The r empirical is nothing but the summation of I going from 1 through n, f of xi not equal to ti. This is the expected value. Y minus eta divided by nu 2 q ti xi. Nu and eta are used to rescale and center the data. So now what has happened is that this maximizing this is equivalent to minimizing this expectation, which is you can approximate it by the empirical average. And now you can use any technique that you want. So in the paper, what he does is that he considers different classification techniques for f, such as support vector machines, just vector, some kind of a QDA, LDA, and then checks as to how this performs out of sample. And it's a pretty interesting, simple paper. Let me see if I can bring that paper up so you can see where that paper is. So he has a bunch of papers on the topic. So if you look at all of these papers, personalized decision making, causal inference with noisy and missing covariates using. So this one is a very different paper. The paper that I was talking about. Yeah, is this? No, that's Martin Udell. This is a follow-up paper. We studied the problem of learning to choose m discrete treatment options, news items, medical drug of the one that best causal effect for a particular instance, user or patient, where the training data consists of passive observations of covariates, treatment, and outcome of the treatment. The standard approach to this problem is to regress and compare, split the data, training data by treatment, fit a regression model for each split, and now for a new instance predict all m outcomes and pick the best. By reformulating the problem as a single learning task rather than m separate ones, we propose a new approach. So this is a nice paper to read. It gives you some techniques that are going on currently. Okay, so that's that. The other area that's become actually very interesting, which is this area of instrumental variables. Instrumental variables are actually a very important technique in causal analysis, and I just want you to know a little bit more about how this might be, how this technique can be used. So the basic idea behind instrumental variables is to see how do we ensure that we have measured all confounding variables. If I know all confounding variables, that means that these are all the variables that make sure that if I measure them, then the treatment is conditionally independent of the outcome. If I know all of those variables, then causal inference is very easy. I can either do propensity score matching, or I can do this idea of stratifying various people and get to a good answer. But we never know that we have picked up all the confounding variables. So is there a way that I can figure that out? So here's the hypothesis, and I'll use this hypothesis as an example. More number of years T of education leads to higher wages. This is true up to a certain point, not unconditionally. So the graphical model that represents this is the following. This is a technique that the joint distribution of Pyt can be written as Pt and Py given T. That is what this graphical model represents. So methodology could be you collect data about number of years people have been studying, look at their wages, you regress y on T, you get beta 0 plus beta 1 T. If beta 1 happens to be positive, you declare that indeed the number of years of education leads to higher wages. What could potentially go wrong here? That even if you turn out to be beta 1 is positive, what could it be? And still this relationship of number of years to education is not true. What could potentially go wrong here? What is a potential factor that might affect both of them? So think about our health example. We put them into treatment condition or no treatment condition. If initially their health was better and more people with better health condition landed up in the treatment condition, you might get a positive effect even though there wasn't an effect. And if more healthy people landed up in the no treatment effect, you might end up getting a negative effect even though there is no effect. So suppose there is no relationship between T and Y. What could cause a positive effect from this regression? What could be the factor that might actually cause a problem here?
Potentially higher earners might have signed up for education.
So you mean there is a relationship from Y to T? No, that's not quite make sense, right? But you have a point. Let's unpack it some more. So it may not be the case higher earners signed up for higher education, but what might be happening?
People with less education do not appear at all in
the wage story?
Yeah.
That's even better, no?
or let's say lesser education.
So let's build a little bit on this idea that higher earners might get higher education as opposed to higher education leading to higher earners. Let's say that there is a latent variable called ability, which can potentially affect the number of years they leave in because they just didn't fail. So they kept going up because at some point they had high ability, they went going up and they did not fail, which means that they have high education. When they land up in the work world, they have high ability to end up getting higher wages, but it's got nothing to do with the number of years that they lived in school that they got higher education, which I think is generally true. It's not clear that if you live in school longer you get higher wages, but it might be a filtering technique. In fact, it's very clear to people that, and maybe this is going to be taped and broadcast, so I shouldn't be too controversial. The fact that you have done a PhD doesn't necessarily mean that you know much more. It just means that you have the ability to go and complete this extended period of education. So perhaps companies should pick you, not because of what you have learned, but because you have figured out how to complete a project. So this might be one of those situations that they're filtering for an ability which has got nothing to do with the number of years studied. Anyway, so what if there is a latent variable x, call it ability, that causes both t and y? So if you look at the graphical model, what happens is that the the relationship between them actually is that there's this variable x that hits y, there's a variable same x which hits both t and y, and that variable potentially can cause problems in our causal estimates. So what we want to do in this instrumental variable is this: we need an instrument, a new variable that can cut off the impact of x. I want to understand the impact of t on y. The problem is that this impact of t and y is being mediated by this x. So I want to create a new variable that somehow breaks this relationship, and then I want to see what happens to t and y. So I want z to be independent of this confounding variable x, which is going to affect people. So I want a variable z that does not depend on x, or that z and x are independent. I want a variable such that t is monotonic in the instrument z. So the amount of studies that you do is monotonically increasing in this variable, and the instrument z is conditionally independent of y. The outcome, wages, is independent of y given the treatment. So the wages that you get given the number of years that you have studied should be independent of this variable. And in fact, there is a paper where, I don't remember the reference of the paper, where they try to use the distance from the university as a measure for this variable z. This paper will not work in India, and probably will not work in the United States, where people travel big distances to go to a university. This paper was built up mainly in Europe, where people stay very local. If you happen to have a town with a big university, you go to that university, get a higher degree. If your town did not happen to have a big university, you don't go. So this paper was using a data where distance to the university impacted the number of years that you studied. And clearly the distance from how far you were born from a university does not have an impact on how much wages you're going to get. So it satisfies that the treatment t is monotonic in the instrument z, and the instrument z is conditionally independent of y given the treatment t. And x, which is ability, typically is not correlated with the distance from the university. Is that true? The ability of somebody will not be correlated with the distance from the university. Well, why maybe? Well, maybe is a good answer. Well, one possibility is, let's say that all the professors of the university actually live near the university. And if you're born near the university, there's a high chance that you were born to some household which is associated with the university. And the ability that we are talking about here doesn't have to be innate ability. It's just if you're exposed to the educational format very early on, you might end up getting. So this last piece, z is independent of the confounding variable, may not be true. But anyway, in this paper they try to use this. So they end up getting this structure. T is dependent on z. X can affect both t and y, but z does not directly affect y. Z is this distance from the university bit. It affects t, and through t it affects y, but it doesn't affect directly y. So you set up a regression. You regress y on t and x. So you end up getting beta 0 plus beta 1 plus beta 2 x plus epsilon. You take t and regress it on z and x. You get gamma 0 plus gamma 1 plus gamma 2 x plus epsilon. We want to compute beta 1 in the presence of x. Note that z is not present on the right hand side of equation for y, because y does not directly get impacted by z. Once I know t, I don't need to know z. And now what we want to do is get a hold of beta 1 without knowing x. X I don't know. These are some confounding variable called ability that will affect the y. I want to allow for the possibility in the regression, but I don't know what this x is, but I want to directly go and compute this t. So what you do is you take this equation and you take the covariance of y with respect to this z variable. So on the right hand side you get covariance of yz. On the left hand side. On the right hand side you get the covariance of beta 0 with z, which is 0 because it's a constant. Then you get the covariance of t with respect to z, and then we have assumed that x and z are independent. So the covariance of x with respect to z is equal to 0. So you automatically get beta 1 is equal to the covariance of yz divided by the covariance of tz. What could potentially happen here is both of them are 0, meaning this Z has no information about T at all, in which case you get nothing. But sometimes you end up getting these instrumental variables which have these correlations, and you end up getting a regression coefficient in the presence of confounding variables. Now this has become, in econometrics for example, some of the most important results right now are basically in this setting, trying to understand how do you do regression when there are confounding variables present which are going to complicate your matters. So, and that's a technique that is becoming really, really important. There's also another area where instrumental variables and natural experiments are showing up, which is very popular in economics. So let's say the hypothesis, you want to test the hypothesis that the severity of incarceration leads to higher crime. This is a very hot button item right now, and in fact this is about the only thing that the Republicans and Democrats are agreeing on right now in the United States, that the prison incarceration rates in the United States are very high and we need to look at it. And one hypothesis would be that if you send people to prison, it actually increases crime or higher crime than if you let them be in the society. Now the question is, how do I go about trying to answer this question? So I need to have some variable like this distance to university business, something that is trivial, that doesn't affect various anything, and yet it's able to give an answer to this question, meaning that I can look at two situations where one variable is by accident different and understand what is going to happen between these two counties. And the areas that people have been looking at quite a bit, which is a very interesting domain, is if you look at two neighboring counties. So take a state and look at in the United States anyway, all laws are done at a state level. So the incarceration rates are by state. You take a boundary county in one state and on the others across the boundary into another state, and let's assume that in these two states the incarceration laws are very different, because these boundaries are typically drawn very arbitrarily. The people living across these two country boundaries tend to be very homogeneous. It's not as if and we are not talking about a country but a state. So if you look at what happens to the crime rates of people who went into and committed initial crimes in these two counties that were same, but they were then sent to different incarceration conditions, maybe one was given a bail, the other one wasn't, one was given community service, another was put into a prison, and now see what happens to these people, you end up getting a natural experiment happening. You randomly assign people into one conditions versus the other, and the randomness happens to be just the boundary of that county that was drawn. And this kind of study has been going on quite a bit in trying to understand how one can do that. Another thing that has become very important is that even within a particular court, two different judges might give very different judgments. So there's a lenient judge and there's a more strict judge. Two defendants come in front of these two judges, and you end up getting that their rate that they end up getting might be very different. And again, that experiment has been starting to be used quite a bit in understanding what is going to happen, to basically using that as a causal analysis to see whether incarceration leads to higher crime. So essentially what you're doing is matching. You are calling one judge as treatment one and the other judge as the another treatment. You're looking at people that are coming into for the same crime, looking at their demographics, and since these two judges are in the same county, if you start matching demographics, the other things about these people, other confounding variables that are there, maybe the education opportunities available to them, the economic condition of the county, all other things will start matching. And from that you can start looking at whether this particular thing about severity of incarceration leads to a higher crime. This idea, question? No.
We are talking about the greedy matching.
Sorry?
Is it the greedy matching?
No, it's not a greedy matching. It is basically the first kind of matching, this kind of. So you match units across you look at two people, one of them went to say a more severe judge and the other one went to a more lenient judge, but on other dimensions they are matched. So you don't do propensity matching, you just try to match, say, their education level, their the part of the county they came from, maybe how much they were earning. But now if you were to take two, say one judge in California and one judge in New York, then you might argue that even though the education level of these people are the same in these two far off places, the opportunities available in California might be very different from the opportunities available in New York. There might be an environment of drugs happening in California which might not be there in New York, or vice versa. There might be, the foster care system in one state is better than the other. There are so many different things you can say, and that is why the crime is being different in these two states. Whereas if this is happening in the same county and the randomness is being generated by a judge, every one of these other opportunities, economic conditions, social conditions are essentially the same. And so you can compare across these units. And the other one is actually by saying that the state laws are different across a boundary, but the people are essentially uniform. Now, typically this will not be true across countries, because the movement of the people across countries is restricted, whereas typically across boundaries in a county the movement of people is not restricted. So if one county becomes very profitable, let's say, people from the next door county will just come over and live there and start making it more uniform. So as a result, you end up getting much more uniformity across counties as opposed to across countries. Now this idea of natural experiments is starting to become very popular in empirical operations management in a big way. So there was a wonderful experiment. Let me see if I can bring up that paper. It's a very nice experiment which is worth reading. Yes, this one. So this is a very nice paper that I would recommend reading. This paper is a few years old. It appeared in 2015, so it's about 2 years old, by Chris Parker. And the idea was that access to information and communication technologies, ICTs, such as mobile phone networks, is widely known to improve market efficiency. In this paper, we examine whether access to timely and accurate information provided through ICT applications has any additional impact. Using a dataset, detailed data from Reuters Market Light, a text message service in India that provides daily price information to market participants, we find that this information reduces geographical price we find that this information reduces the geographical price dispersion of crops in rural communities by an average of 12% over and above access to mobile phone technology and other means of communication. So basically what they were looking at was, you looked at different markets, and if you did not have this information available to you, typically farmers went to the nearest market to sell their product. But if you had this market light information available, then they had information about the prices in different markets, and so you went and took your goods to the market which gave you the highest price, and as a result the prices of these markets tend to become closer to each other. They are not sustaining differences. To identify the effect of information on price dispersion, we exploited a natural experiment where the bulk text messages were banned unexpectedly across India for 12 days in 2010. Does anybody know why that happened? There was some political event. We find that besides reducing geographical price dispersion, RML also increases the rate at which prices converge across India over time. So let me show you this paper, because it's actually, I don't want to register. Let's see if I can get you that paper. It's actually, I don't remember what it is, but it was a fascinating thing when I read.
So the event was Ayodhya verdict.
Ah, that was it?
2010, Allahabad court's verdict.
Yes, you're right. So that's where it says here.
So bulk messages were suspended during that period.
Yes.
Due to the verdict.
So September 23rd, 2010, RML experienced a major service disruption when bulk text messages were unexpectedly banned throughout India in advance of a High Court verdict that was to be announced on September 24, 2010. To reduce the likelihood of rumors spreading via text messages and technology coordinated riots, the government directed telecommunication providers to immediately disable bulk text messages throughout the country on the evening of September 22nd. The ban was lifted on the night of October 4th, 2010, and operations for RML returned to normal on October 5th, 2010. So for 12 days of the ban, RML collected price information without being able to transmit it. So this was an interesting experiment that happened. So all the other conditions were the same, except that this text message was missing. And there was also another very important factor. People could not predict that this will happen. Because suppose, it is very important in this, suppose the farmers knew that on September 22nd, 2010, the government for 10 days will ban text messages. Then you could say that their behavior in that intervening period had already taken into consideration that this event will happen in the future, and therefore it's not really an abrupt experiment. On the other hand, this was something they probably knew that it was going to be announced on September 24, 2010, but they did not know that the government will ban the bulk text messages. So this became a very nice natural experiment. And like they say over here, the ban resulted in an unexpected exogenous shock to the service provided by RML. And this is something all other forms of, including visiting, calling markets, and what they were trying to look at was whether this text message made a difference. And the other thing that happened was all other sources of information retrieval, visiting, calling markets, sending personal text messages, asking families, friends, fellow market participants, even checking the prices through internet or internet enabled kiosks, were unaffected by the ban. This provides an almost ideal natural experiment that alleviates endogeneity concerns. And this is something that's, this kind of trying to look for these natural experiments that are happening, it's turning out to be an important place where people are trying to get at causality through these experiments. Another area where these kinds of experiments are starting to play an important role are in the internet, internet advertising. And there what people do is, just because of the natural randomness in the way customers are going through the system, there are experiments happening in the sense that some people are being exposed to one kind of ad, some other people are being exposed to another kind of ads. So in a way, implicitly, A/B testing is happening along the way. And is there a way that we can leverage that A/B tested data, sort of along the same lines as what Nathan was doing in his modeling? If there is a way that we can extract that A/B tested data, can we answer questions of causality which are not answered so far? All right, so that's the end of my module, and I was hoping to get a little bit more time with you, but I guess we'll stop here. Thank you so much.